Okay, last topic for the week and for chapter 13 is polarization. So we have seen through Young's double slit experiment that light is definitely a wave. But you'll remember from physics 20, there are kind of two types of waves, right? There's transverse and longitudinal, where transverse is when the direction of propagation is perpendicular to direction of oscillation. So that would look like this, okay? So as the wave travels this way, as v goes that way, the oscillation direction would be like this, right? And we've kind of seen that's a transverse wave, but that's kind of with a modern understanding. We actually haven't looked into how we know that yet, right? But we know that the electric field and magnetic fields will be going from up to down, up to down, up to down, okay? So spoiler alert, it is a transverse wave, but let's look at what longitudinal, let's remind ourselves what longitudinal meant, okay? That was when the direction of propagation is parallel to the oscillation. So that would look like a compression wave, okay? So where we have compressions and rarefactions. So like sound, that was a longitudinal wave. So as the wave moved this way, the particles moved that way as well, right? They compress that way and then they rarefact the other way. So how can we figure it out with light? Well, something that we can do to light tells us it must be a transverse wave, okay? So we can use something called a polarizer. Now we briefly mentioned this before, but if it's unpolarized, it's essentially oscillating in all directions, or at least in more than one direction, okay? So unpolarized light is made of many rays, each with electric fields oscillating in many directions, okay? So look at an image here, but I just want to be careful. The magnetic field component of the EMR, of the electromagnetic radiation, has been left out of the diagram simply for just to make the diagram a little bit simpler and nicer to look at. It is, of course, still there. Otherwise, the light would not be propagating, right? You need that electric field feeding the magnetic field to feed the electric field for it to propagate. So don't be fooled by this. This is not how it would actually look. They've just completely left magnetic fields out here just to make it nicer to look at. So this is what unpolarized light looks like, right? Each of these electric field components in realistically 360 degrees going around. So it would actually look more like a tube, right? They've just drawn a few. So each of them does have their own magnetic field. Don't forget that. We can pass it through something called a polarizer. What a polarizer does, it's essentially a film made of long molecules that form basically bars across the polarizer, okay? And so they only let light pass through if it's oscillating in a certain direction or within a certain angle at least, right? So they only let light through, in this case, that is oscillating like this, up, down, up, down, up, down. And so all of this other light, any other angle gets blocked, and only this light is now able to get through. What's going to happen when they hit this polarizer that has the opposite orientation, that has a perpendicular orientation? Well, this can't get through. This is the exact opposite of what can get through this guy. So all of the light is going to get blocked. Okay. So again, just highlighting here what happened above. So light with an electric field oscillating in one direction gets through a polarizer. Now, if we come down to this diagram here, okay, when two polarizers are parallel, light that traveled through the first is still able to travel through the second, right? Of course it is, because if it got through the first and the second has the same orientation, well, it already passed this test, right? It's going to keep going. It's oscillating in the direction that this polarizer would like to polarize the light anyway. However, when they're perpendicular, like in the picture above, the light that traveled through the first polarizer, it's now polarized in the orientation to get perfectly blocked when they are perpendicular, okay? So again, there's a good analogy we can use here of a rope between two kind of picket fences, right? So for a second, just block this one out, right? Imagine over here, so in place of an accelerating charge to produce EMR, it's your hand on a rope going up and down and up and down. What if you were going all crazy in all types of different directions? Well, the only time that wave would be able to transverse through is in when your direction happened to go up, down, right? And then that wave would be able to pass through this fence. But if you went side to side, this fence would block that wave and it would not allow it to get through, okay? Now, if the next fence is oriented in the same way, then yeah, that wave just keeps on moving through, up, down, right? But what if you now have you're going to let only the up-down oscillating electric fields through for this first one. Even if you go side to side, they're not going to get through this first guy, but the up-down ones will. But then the next one you have is oriented at a perpendicular angle to it. Well, whatever got through here automatically can't get through here, right? It's not going to allow up-down oscillations through. And so that's kind of the analogy that we use here, right? And so as it comes through, up, down, and then this one is oriented parallel to it, so it gets through just fine. But here, when you do it perpendicular, up, down gets through. But this one, up, down is the main type of light that it's not letting through. It's set up to let side-to-side light through. And so, of course, light does not get through the second. And that means no light is getting through at all, because whatever you let through here is now going to get blocked here. So only a transverse wave can explain this phenomenon, right? This picture does a good job here. If you had a longitudinal wave, what's the problem? It can compress and rarefact through a vertical one, and then it can compress and rarefact through a horizontal one. There's no problem there, right? Imagine a slinky going through a fence where you're sending compressions through. The orientation wouldn't make a difference. However, if light is indeed a transverse wave where the direction of oscillation is perpendicular to the direction of propagation, then you will indeed see only one type let through a polarizer like this, and then that type, if you have it perpendicular, will be perfectly blocked. Okay, so what are some applications of this? Well, what I have here are two polarized camera filters. Why would we want polarized camera filters? Well, if you've done any photography, you'll notice that if you're taking a picture, for example, of water or of through glass, okay, what a polarized filter can do is remove a lot of the glare. That's because when light gets reflected, it actually gets polarized a bit in the direction of where it's coming in and going out, right? Think of like a basketball kind of coming in, compressing as it hits. The light kind of gets stretched as it hits, and it gets more polarized this way. Okay, so if you have a filter that only lets light in through the right orientation, then you can block out all of that polarized light, and you can get a nice picture of the unpolarized light coming from, for example, behind the glass or through the water or something. You can take glare off. This is why sunglasses are often polarized. They reduce the glare of the polarized light bouncing to your eye, and they kind of take away some of the edge. So here, again, I have these two polarized camera filters. Okay, so I just got my phone light here. Okay, just pointed at you guys. Now, if I put the polarizing filter over it, you'll notice light still comes through, but it is a little dimmer, right? Why would it be dimmer? Well, not all of the light is now getting through, right? Only light that's oscillating in the direction that this filter is set up to let through is now getting to you. So, but still a good amount is getting to you, right? It's still fairly bright. I'm going to take another polarizing filter, right? You can see, okay, same idea, okay? I'm going to take another one and place it in front, okay? And still, it gets a little bit dimmer, but for the most part, light is getting through, right? Watch what happens though. I'm now going to take this front one and I'm going to rotate it 90 degrees. I want you to watch what happens as I do that. Look at that. So look, at that point there where the polarizing filters are being held perpendicular to each other, notice no light at all is getting through, because this one is letting through light polarized this way, and this one is letting through light polarized this way. So when you put those together, they don't let anything through, right? And then I can bring it back if I keep going, right? Back to most light being let through where they're parallel, okay? Getting brighter, 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 parallel, and then dimmer, 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 dimmer as we head back to perpendicular. Pretty cool. Okay, so hopping back to the notes here. Again, why do polarized glasses reduce glare? Because reflected sunlight is polarized, and blocking that allows the original image through still. So you can see the light, but you don't get blinded by that polarized, reflected light. Okay, now recall the antenna that we talked about. Was the EMR that was produced polarized? Now we said yes. Okay, now we can understand with a bit more depth why. So in an antenna, you'll recall it was just an electron basically going up and down, up and down. So yes, the electron only accelerated, not moved, but accelerated in one axis, okay? So why did that produce polarized light? Well then, therefore, the change in the electric field was only happening in one axis, right? The change in electric field was only happening up, down, and so we were getting these polarized waves out. Polarized EMR was the result. Okay, just a couple application questions of this. So we have four possible orientations of two polarizers that have light incident upon them, okay? So they are polarized. This line here kind of means that's the type of light they will let through, okay? So it's asking us here, list the orientations in order from the ones that transmit the least to the ones that transmit the most amount of light. Transmit again means let through. So in the case that they tie, just list them in numerical order. Okay, so let's take a look. Let's see. What would let the max light through? What orientation? What would need to be the angle between their orientation axes? Well, it would need to be 0, right? They would need to have there would need to be no angle. They need to be parallel to each other. So looking at this one, there's going to be a little geometry involved here, okay? From vertical to the angle that it's at is an angle of 30 degrees, which means from here to here would be 60 degrees, right? Why am I finding that angle? Because this one is horizontal, right? So that would be a 60-degree angle. So these ones have an angle of 60 degrees, okay? What would let the most light through again? We said would be 0 degrees. What would let the least light, in fact, pretty much no light through? A 90-degree orientation relative to each other, right? Perpendicular. So 60, it's not going to let a ton through. Let's look at the other ones to see. Okay, so what angle are these at relative to each other? So if this angle here is 30, okay, well then the angle to the vertical here must be 60, okay? This thing is at an angle that way of 30. So from this one to this one is 60, and then on the 30, hey, 90 degrees. Okay, that one's gonna let no light through at all. Okay, look at this one. We have light incident on this one that is tilted off of the vertical axis by 30 degrees. This one's tilted off the vertical axis by 30 degrees, but the other way. So the difference here would be 60 degrees. Okay, let's just call the difference delta theta. So 1 and 3 are actually going to be tied. They're going to let the same amount of light through. Okay, let's look at this one here. So the angle from its polarization axis to the horizontal is 60, which means the angle to the vertical would be 30. So these one, since this one is vertical, that means they have a orientation difference of 30 degrees. Okay, so to go from least to most, right, we go from most perpendicular to most parallel. So most perpendicular is obviously the one that's actually perpendicular, 90 degrees. That will let pretty much no light through. So 2 is definitely the least. So what's the next closest to perpendicular? Well, we have a tie here between 1 and 3. Both are at 60 degrees, so they don't let much through, okay? So 1, so that's a tie, so we'll go in numerical order, 1, 3. And then the most light transmitted is the one that's most close to being parallel. So since 30 degrees is the smallest angle here, we have 2, 1, 3, 4. Okay, another picture here of some light being polarized. Again, they have just left off the magnetic fields for simplicity. The magnetic field still exists here, right? Light cannot propagate without its magnetic field component. Otherwise, you just have an electric field that does not keep going. Okay, so essentially just a knowledge question here. Match the description above with the quality below that best describes the nature and behavior of light. So a lot of this doesn't even have anything to do with polarization. The type of wave, so is it longitude, transverse? I mean, parallel and perpendicular, those aren't types of waves, so it's either longitudinal or transverse. We know that the fact that light is polarizable means it must be a transverse wave, right? Again, picture the fence with the rope. If it was a slinky, you could put a longitudinal wave through the fence no matter what their orientation is. However, if it's transverse, polarization will come into play. So that means light is a transverse wave, okay? Just some knowledge about the nature of EMR here. What's the direction of the magnetic field relative to the electric field? Well, we know they're always perpendicular, right? Always perpendicular to each other. In fact, they are in a three-way perpendicular relationship because the direction of propagation is also perpendicular relative to the magnetic field. So again, perpendicular, right? If your electric field is oscillating up and down, your magnetic field could be oscillating into and out of the page, and then your propagation would be left to right. Okay, the second polarizer's orientation relative to the first two allow light to pass. So if we look at this one, right, that is not letting light pass, right? This light would not be able to get by because this polarizer is oriented to let vertically polarized light through. This one is oriented to only let horizontally polarized light through. So this ain't getting through, okay? But just in general, you have to orient your polarizer parallel to your first polarizer if you're going to let the light through. Side note, yes, polarization proves that light is a transverse wave, but it also just proves it's a wave. You can't block particles like this, right? So going back to the fence, right? Imagine you're spraying, let's say, water particles at this. Well, they're going to get through the cracks there. They're going to get through the cracks there. If you turn it sideways, yeah, some of it's going to get blocked, but a lot of it is still going to get through both cracks, right? You're going to kind of get like a tic-tac-toe shape coming out of there. So yes, light showed that it's a transverse wave, but kind of by extension, it showed that it's just more evidence that light is a wave. Okay, that wraps up this week and chapter 13. So you can go check the agenda or Google Classroom for which questions to try with this topic. Have a great weekend.